Hello and welcome. I hope you are having a great day. In this video, we are going to discuss about Bayesian point estimators. In last video, we discussed about parametric model estimation, and one of that was we discussed two philosophies: frequentist method and the Bayesian method. So the complete discussion was done in the last video. So that will be a prerequisite for that video. Watch that video and come here. Only then it will make sense, or it will make more sense. Okay. So that's the requirement for watching this video. Watch that and come here, and we'll extend the discussion that we are doing in the last video. And we learnt in the last video that for estimating what will be the parameters which describe the data that we have, that is parametric model estimation, there were two methods: frequentist, under which we studied MLE, maximum likelihood estimate, and then the other one was Bayesian, which gave us, so in MLE we got a 1 point value. So the parameter was unknown, but it was fixed. Okay, so the parameter theta was fixed according to MLE. And the Bayesian, how did it do? In the Bayesian approach, what did we do? We considered that the theta itself is a random variable. The parameters of the model are not fixed, but they are a probability distribution. Okay, so we approach that way because whenever we have few less, the sample size is small, we can use this information plus the prior information or the initial belief to make a good estimate of the parameters of the model. So this is very helpful. This Bayesian approach is very helpful when the sample size is small, when the data set what we have is small. So we will continue that discussion. So what did Bayesian approach say? That the parameter is not a fixed value, not a point estimate, but a complete probability distribution. We model the parameter as a random variable with its own probability distribution. So let me write it down for you so that you remember what was the Bayesian approach. So the Bayesian approach, it said that that we had the prior, okay, and this said that theta is a random variable with a probability distribution. So whatever, depending upon our initial prior belief. So most of the times we knew, right, what would be the underlying distribution. We knew that, and we made a prior assumption. As we saw in the last video, we made an assumption that it was a Bernoulli. Say for example, if we have a case that we know that initial distribution is a Gaussian, so we will know the mu and sigma of this, right? There will be mu and there will be a sigma, the standard deviation. We'll know about this, so we can use this. So we'll have, but we have to find these parameters. What would be the mu and sigma of the realizations or observations that we have, or the data that we have? What parameters best describe this data that we have seen? And Bayesian approach, what did it do? It uses the Bayes theorem. So based on the prior information plus the likelihood, we calculated the posterior distribution. Okay, and we'll continue that thought. So the posterior distribution, so what was the Bayes theorem? Let me write that down for you so that it's according to the Bayes theorem. So we have discussed this in detail in the last video. Let me just write it. Okay, so just P of theta, this is capital theta, given x is equal to P of theta into P of x given theta by P of x. Okay, so this is my posterior. This is the prior. What is the initial belief about the parameters? Okay, what is the distribution? And this is the likelihood. Likelihood means the likelihood of seeing the data, the sample that we have observed, given the parameters of the model. So this is the likelihood. So we have this now. In how to calculate, how to estimate this, we have seen this. So once we have this posterior, so we get a complete distribution, probability distribution. But the question is, what if what see the topic also. What if you want just one point estimate, not the complete distribution? So what will be those point estimate? So as we did for MLE, right, we want one value, okay, which will be a representative value of the complete distribution, as we have mean, etc., right? So if you want a representative variable value which will describe, okay, which will be the representative value, that what is the value of this complete distribution, we want one parameter. So what we will do after getting this, so once we have described, okay, so once we have the distribution, once we have estimated the posterior distribution of random variable theta, okay, we want to have a single point estimate, as in MLE, maximum likelihood estimate. So this is the task, that the task is to have a single point from that distribution, and we'll discuss the two most popular methods. One is maximum A posteriori map estimation, and then minimum mean squared error estimation. So these are the two. What are the two? When to use which approach? We'll discuss that as we dive deeper into this. So let's start with the first point estimator, that is MAP, commonly known as MAP, or maximum A posteriori estimate or estimation. So let's start with that first point estimator, maximum. By now you must have understood what is the meaning. A posteriori, that is what is MAP estimation. I'll write it in bracket here itself, MAP. A posteriori means after we have got the posterior, there will be I. So this estimation we get after we have got the posterior distribution using the Bayesian approach. Okay, so we have a prior, and then we have the initial likelihood, and all these calculations we have seen in the last video. So once we have that, how do we do this? Okay, so what does it do basically? What is the theory behind this? So maximum A posteriori estimation, what does it do? It finds the peak of the, say for example, we assume that this is a Gaussian. So there is a Gaussian. Okay, so this will find in Gaussian the mu is also the peak or whatever. Okay, so this peak value, so if it is Gaussian or perfectly symmetrical, right, the peak coincides with the mean. Okay, but then all the distributions, it may not be the same. So whatever is the peak value, say for example, even if it's skewed like this, right, so the peak may not be the mean. Okay, the mean will be somewhat on this side, and it may not be the mean. Okay, so that's the case. So whatever is the peak value, so the peak value tells me the mode of this distribution, because most of this is a PDF, right? This is a PDF. So the peak here, this peak will tell me that what is the value around which the probability of finding something is maximum. This is a probability distribution. So at this value, whatever is the peak, so we'll have the maximum number of entries. That's why the probability is high here. So this is your mode or the peak. The peak means mode. Mode means which entry has the highest count. Say for example, what is the mode? Let me do a revision of the mode. Say for example, I have a set like 1, 2, 3, 3, 3, 5. So what will be the mode of this? Mode will be equal to 3, because 3 is multiple times. And even if I do a PDF or PMF like this, so 3 will have it will pull the mean towards it, and 3 will have the highest peak here, because the value around 3 means 3 has the maximum number, and it will pull it around. The mean will be there, or the peak will be around this, the PDF. So this is what it means. And the map estimate gives us this mode or the peak of the curve. Let me write it down. So it gives, this finds we will use this to find the peak or mode. I hope this peak and mode is clear. Okay, peak or mode of the posterior distribution. Okay, so let's begin. So this will be represented as theta map, as we did theta MLE in the last class. So this will be equal to find the parameter theta, which is a maximum A posteriori estimate. This will be a point estimate for which maximizes my posterior distribution, argmax theta, which will maximize my posterior distribution, theta given x, theta given x. So this will be f or p depending upon whether it's continuous or discrete. So for example, if I'm using this is a continuous, then I'll use f, and if it is discrete, I'll use p. Okay, so this is a symbol. So this is my posterior distribution. So I have to find that theta which will maximize this, and this maximum would be around the peak of that posterior distribution, wherever I get, like this. And this is there, or it can be this way, then this is here. So I have to find that peak. How will we do that? Let's see now. This is for continuous. Okay, so this is posterior, and this is for continuous case. Let me write it down so that the symbols are clear. And this will be equal to argmax of theta, probability theta given x, theta given x. This is your capital theta. Okay, this is a capital theta, this is small theta. This is capital X, this is small x. Okay, and this is for when theta is discrete. Theta continuous, and where theta is discrete. So I'll have P. F is for the PDF of continuous random variable. So now let's understand. So these terms are clear. So let's see an example of Gaussian distribution. Last class we saw Bernoulli. Let's do a Gaussian, which will make it more clear, and the maths would come out more here. Okay, so it will be more complicated with respect to maths, but you will understand the fundamentals better. So let's do it. For example, so we have a distribution, so we know that x is a Gaussian, and we want to estimate the parameters of that. So this is a Gaussian with n, theta, and say we know the sigma square. Sigma square is equal to 1. The variance we know. Okay, and we want to estimate this. This is unknown. This is unknown parameter. So we know that the data is coming from a Gaussian, but we don't know the mean. This is the mean of the Gaussian. Okay, but we know the variance. Variance is 1. To make the problem simple, we will estimate only one parameter. So let's move on. So what's the, and let's assume that this is the underlying distribution of the data that we assume, and then that's what x1, x2, similarly xn or random variable Gaussian. Okay, so let's do case by case. So let's see, there's a first case as we did earlier. First case, we'll start with a uniform, get a distribution, get the parameters value, and then we will see when the distribution is not uniform or it is biased towards. We have some prior knowledge in the last case class we saw, right? The theta was uniform initially, and in the other case the theta was equal to 2 theta, that it was biased towards 1. So theta was 0, 1, it was Bernoulli trial. So theta was more biased. We had the prior belief or prior that theta, in the first one theta was uniform, 0 and 1 are equally likely. Other case theta was 2 theta, means it is more biased towards 1. Similarly here also in the first case we'll see that theta is uniform. So we'll start with that. Okay, so here we'll assume that P of theta 1 is equal to P of theta 0 is equal to half. Both are equally likely. Okay, and let's model it as discrete. It was Bernoulli, we modeled the prior as a uniform continuous. Here it is Gaussian underlying distribution, and we are modeling the prior belief as a discrete. Okay, just to say show you that continuous and discrete can go hand in hand. It's not like the problem should be complete continuous or complete discrete. Okay, so this is the belief. So let me draw the PMF for this. Say for example, this is your PMF, and say this is 0 and this is 1, and say this is your half mark, this is half or 0.5. So you will have to, so this is not a earlier uniform. If it was uniform you will have a straight line, but PMF the probabilities are concentrated at points. So here you will have one concentration at 0, and here you will have one concentration at 1. Okay, so both are half of. This is our PMF. PMF for the discrete initial belief that both 0 and 1 are half of, equally likely. So this is a prior. This is a prior. The next, so for calculating posterior we need prior, then we need likelihood. So what will be the likelihood? Likelihood, we know it's a Gaussian. So what is the PDF of a Gaussian? Earlier it was Bernoulli. So this will be f of x given theta, x given theta is equal to, so PDF of Bernoulli would be, so it's the product of all. So it will be pi equal to 1 to n 1 by root 2 pi sigma e to the power minus xi minus mu whole square by 2 sigma square. Okay, this is our e to the power minus, this is our Gaussian. By now you should be used to this. Okay, Gaussian. So we know that sigma is equal to 1. Let's put this in this, f of x given theta, capital theta, x given theta is equal to pi I equal to 1 to n 1 by root 2 pi, this sigma is 1, so I'll let it be, and e to the power minus xi minus mu whole square. There will be nothing in the denominator. No, it will be 2. There will be 2 sigma square, there will be 2. Okay, the sigma square is 1 here and the sigma is 1 here, because that is initial. This is how what the distribution is we have started with. So what is the problem about? So we want to find the distribution. It's the Gaussian, we know that. So it's a Gaussian, and the mean is by either 0 or 1. Okay, so we know that. So the mean is either 0 or 1. It's a Gaussian with mean 0 or 1, and probability of having mean at 0 or 1 is equally likely. So how will this distribution be? So it will be something like this: one peak around 0, another peak around 1. Okay, so we have to find out what is the distribution like, whether it's this distribution or this distribution, either of these two. Okay, if theta is 0, so because only there are two possibilities, theta is 0 or half. That's how we have formulated the problem. So either my distribution is this or this, and you have to find out which one is it. Okay, so this is our Gaussian. So this is, I hope the problem is clear, and then let's proceed. Let's do the maths. So this is we had the prior, that probability of seeing theta is our mean, right? This is the theta mean, mu, at 0 or 1. Okay, likelihood, this is the likelihood, this is the Gaussian formula. The prior is 1, this is the likelihood. And now posterior, let's calculate the posterior. What will be the posterior based on the Bayes theorem? Posterior will again be it will be a distribution based on the prior. So whatever is the prior, my posterior will depend on that. So if it's a discrete, then my posterior will be a discrete. Okay, so what will be the posterior distribution? P of theta given x is equal to P of theta into, here it is f, it's a continuous because fx given theta, x given theta by fx of x. This is the, let me write it down here also so that you remember. This is just a revision of what we have done. This is Bayesian. Posterior, this is my prior, this is likelihood. Okay, and this is the evidence, or this will be my marginal probability. Okay, all these terms, that is clear. So we have this is the initial belief. We know the distribution is Gaussian. Okay, that's the, we have to find the parameter theta. So given this theta, it is a Gaussian, and we have to find the parameter after seeing the data. What is my actual parameter now? We have to find that probability. Let's do. We need to find, and we have to maximize the possibility of seeing that data. That's what the parametric model estimation means, right? So if I have to find such theta which will maximize the probability of seeing the data that we have seen, this x1, x2, xn, all this is the data we have seen. This is the data, right? Or the observation. So this will maximize the probability of seeing such a data. We have to find such parameters of the underlying model. Okay. So calculating this is the probability. This is the PDF of the underlying distribution, right? That's what we are trying to, but we don't have this information. This is the hardest part. So generally we try to get rid of this or try to solve it in another way. We don't know this. So this is a hard problem. Getting this value. This is hard. Okay. So we'll see ways. Earlier also we have seen how to, we use beta distribution, and then we'll see how to get around this problem. So let's see. So we need to find, so this is a product, right? So we have seen this. This was a product. Let's write down, and then let's do it as a, let's take a log on both the sides. So we need to find this. This will be difficult. So for solving this, let's take a log on both sides. Okay, log on both sides because computing this will be very difficult without the parameters. We don't know anything. That's what we want to estimate. So this will be log of, okay, posterior, log of p theta given x, theta given x is equal to, so this is a product, the log of a into b by b. So this will be log a plus log b minus log c, the denominator. So log of sorry log of p theta plus log of the likelihood, that is f of seeing x given theta, and then minus of log of f of x of x. Okay, and the task is find theta that maximizes the probability of observing the data. So we have to find the theta max. So this will be like, we need to find max, R max theta. We have to find sorry p theta given x, theta small x, which will maximize this probability. We have to maximize this probability, and log is a monotonic function. So log of, if x increases, log x increases. Okay, this is a monotonic function. So that's why I've taken log. It doesn't change, but it will make our math simple. So we time and again we'll be taking log in everywhere because it will make our math simple. It will convert the product into sum. So let's find out. So what we do. So now generally when we try to find the max of something, what did we do earlier? We'll take the first derivative and equate it to 0. That will be our point of optima, maxima or minima. But here taking the derivative of this and equating it to 0 will be very difficult. Okay, because and also we don't need to do that. We can have a simpler way to solve this. Okay, because this part is the difficult part, because we don't have, this has nothing to do with theta also, first of all, and again differentiating it with respect to theta, this will again go to 0. But we just need to find, we have two values. So why to differentiate and find all the possible values where it will be. So here our prior says that my theta or the mean is either 0 or 1. So there are only two possibilities. So we can directly calculate the two possibilities and compare the values instead of differentiating and going that harder way. So that will make our task easier in this case. So what we'll do is we'll check for only these two values, theta at 1 and theta at 0, because that's what we have to find, that theta has only, this is the mu will have only these two values, mu is equal to 0 or mu is equal to 1. These are the two possible. That is the prior belief we had. These are the only two values. This is the distribution. Okay, so what we'll do also, when we want to compare with two values, also this fx of x doesn't have any theta, and computing this is difficult, so we can get rid of this when we compare two values, right? And this value is common in both of them. So when we add or subtract the same thing on two terms, it doesn't make sense. It doesn't add any value, so we can ignore this. Say for example, if I'm comparing two values, say 5 is greater than 3, right? If I subtract 2 from here and 2 from here, it will be the same thing. 3 is greater than 1, the equality or inequality remains the same, right? That's what we want to do. So this is your extra part. So I want to get rid of this. I don't want to calculate this. Okay, so that's why we have done. So let's move on. How do we do? So we have two values. We want to calculate at 2 points. Log of probability of theta given x is equal to log of p theta of theta plus log of x given theta minus log of fx of x. Okay, so we will put theta equal to 0 and we'll evaluate it theta equal to 1. Okay, so let's evaluate. So log of probability of theta given x, and let's put 0. So first we'll put 0 given x is equal to log of p theta p theta 0 plus log of, what is the distribution? So with the distribution we had, right, for the Gaussian f of x, this is the distribution, log of this term plus log of 1 by root 2 pi, okay, e to the power minus x minus mu I whole square by 2, and minus log of fx of x. This is the similarly. So here instead of mu I, this will be 0. I'll put all the values wherever theta is 0. Mu was 0, and then we'll have log of p of theta given x, 1 given x, seeing 1 given x is log of probability of 1 plus log of 1 by root 2 pi e to the power minus x minus 1 whole square by 2 minus log of fx of x. From now on, both the sides are having this. I won't consider this value. Sorry, I won't consider this value. So this is common in both the sides. I want to compare. Now either of these two terms can be greater, this or this. Okay, so let's assume that theta equal to 1, that is the greater term. Okay, so for this value to be greater than this value, okay, what should be the case? Okay, if this is greater than this, so let's put down the value. So what should be the case? So here I'll put it. So this is theta equal to half. So this value we know. This is theta 0. Probability of theta is 0. Is that the prior belief? Both are same. P theta 1 and P theta 0. Sorry. Both are same. That are half. This is equal to half. This is equal to half. We know that. and we'll expand the second term also. So this is same for both the cases. And now for this, for one case, for theta equal to 1 log of p theta given x, 1 given x should be greater than, if I want that this is, that one side is greater, assuming, what will be the calculation be like? Log of p theta given x, 0 given x. Yes, sorry. Okay, let's continue. So what will be this value? This will be equal to, this second term. So here, if you see, this is common, I'll cancel this out. Okay, this is common in both, this is also common. So only thing that compares is this value, log of the Gaussian part. We'll compare this, and I'm assuming that this is greater than this. This value is greater than this value. Okay, so for this to be, for theta to be 1, sorry, not log. So there are only two possible values. So for theta to be 1, if this probability is greater, means log of some probability is greater, then this theta is equal to 1. I have to calculate either or this value. So whichever value calculates greater, that will make that I can choose 1 as the value. And if this becomes greater, then I can choose 0 is the probability. So I have to find out which one comes there. Okay, so let's see. So what is this coming to? This will come by, so this will be expanded. So there will be some maths, follow along. Okay, if not, just do it on your own later. So this will be again, this was a product, right? This was pi I equal to 1 to 1. This was a product n times. Okay, so this will become, to the power n will be there. So I'll just make it simple. Okay, so this will be, so what will be this one? So this, let me just expand this Gaussian term, log of 1 by root 2 pi minus x minus mu I whole square by 2. Okay, so this whole term, so this will be there, product of this plus, okay, this will be coming n times, this will become power n. Okay, and when I take log of this n will come outside. I'm just giving you one hint, and then rest of things you can just figure out. So this will come multiplied n times, so this will become n times outside. And when I take log, that power n, okay, this thing multiplied n times will become, its power will become n, right? And I take log of this after doing this pi. Okay, if I take, so it will become n log, so n will come in front, this will become n log 1 by root 2 pi, the first term, and then log and exponential will cancel each other, right? So it will become, and this whole product will become a summation, the second part. Okay, the second part. So this is a product plus this exponential will cancel out the log, and plus this product will become summation. Okay, I equal to 1 to n xi minus mu whole square by 2. Okay, I hope this is clear. And because of this minus will come here. This minus is there, right? This will cancel out only e. This minus will come as it is. So this will become e. This will become minus here. I hope this is clear, how I have taken log of this. Right? So this product, this has power n, so this n came here, and this product of this made its summation, and e was cancelled out by log, and the rest of the term came as it is. I hope the maths is clear. Okay, so let's see again. So if you see this n log root 2 pi, okay, n log 1 by root 2 pi, this is common, this will be common for both, because this term is common here, this is here and here also. Okay, pi I equal to 1 to n, just for this, and here also I'll write mu mu I. So this was 0, but I'll, okay, 0. That doesn't change anything. Okay, so this is here. So this term, what I'm saying, is common in both, so I can get rid of this also. Okay, so let me write it down again so that it's clear for you, all the terms together. Log of probability of theta given x, of saying first, okay, 0 given x, is equal to log of p theta, that was half, plus log of 1 by root 2 pi minus log of, okay, minus this log, and this will cancel out, so this will, log will go off. So that second term from here, sigma I equal to 1 to n xi minus 0 whole square by 2, and fx we have already got rid of, and then log of p theta given x, 1 for case 1, this will be again, both cases are half, plus log of 1 by root 2 pi n times, okay, minus, I'm just missing it because both are same, so it doesn't matter, not x, xi, this will be there by 2, okay. Both are same, fx already got rid of, and this is also same, so I'll get rid of this. So only thing that remains is this and this term. So for this to be greater, so for theta to be 1, for theta equal to 1, if I say that theta is equal to 1, so this probability should be greater than the above probability, means this term should be greater than this term. So this term should be greater than this term. So finally this will come as, for theta to be 1, minus sigma I equal to 1 to n xi minus 1 whole square by 2 should be greater than minus sigma I equal to 1 to n xi minus 0 whole square by 2. I hope this is clear. For theta to be greater than 1, for theta equal to 1, for theta to be 1, not 0, this term should be greater than this term, only then this will hold. Okay, let's continue. So this implies, what will be the case? Sorry. So I'll bring this term also here. Okay, this will become sigma I equal to 1 to n xi, let it be xi only, xi square by 2 minus sigma I equal to 1 to n xi minus whole square by 2 is greater than 0. Okay, so what will be this equal to? So I'll just keep sigma I equal to 1. Okay, and this 2 half will be common, and this will be coming sigma n times, so 1 by 2n will be common in both. Okay, because this summation n times will become n in both, so I'll take this 2n common and bring it out. And let's expand it, xi square, and what will be this? Minus xi square minus 2xi plus 1 is greater than 0. So this implies 1 by 2n. So this will be, this and this term will cancel out because that's negative, and then remaining minus minus plus, this will become 2xi minus 1 is greater than equal to 0. Okay, so this is equal to this implies that sigma again. Okay, so let's do the maths. Sigma, okay, I equal to 1 to n, this is for all, I equal to 1 to n, this is 1 by 2 n times, okay, and this will be 2xi, this will be 2xi times. So let's do a separate, so this will be sigma 2xi minus sigma I equal to 1 to n, this will become minus n. Okay, I have done this summation, so the sigma remains here, sorry, the sigma remains here, the 2xi, and this will be greater than or equal to 0, and this implies what will be the value. So this will be here 1 by 2n and this n, so this will go out. Okay, so let me, this bracket will hold, so sigma I equal to 1 to n 2xi, this will be 1 by 2n minus n by 2n is greater than 0. This n and n cancels out, this implies, so I have just opened the bracket. Okay, so this will be sigma 1 by 2n 2xi is greater than 1 by 2. This 2 and 2 will cancel out, this is I equal to 1 to 1. This implies 1 by n sigma I equal to 1 to n xi is greater than half. This was n and n by 2 has come this side, right? So this is our final conclusion. So what is this value? 1 by n sigma I equal to 1 to n. We have seen this in the past, right? This is your nothing but, this is the mean. Sum of all values divided by the number of terms. Sum of all the terms divided by the number of terms. This is the mean. Okay. So how can we write, so our theta map, what will be my theta map? Should be greater than half. What did we assume? That for theta equal to 1, what should be the condition? For theta to be 1, my theta map should be the average, the mean should be greater than half. When, so I said that mu I is either 0 or either 1. So if summation of all the values, if it is greater than 0, means it is 1. And if it is equal to or less than 0, okay, then this will be 0. So what will be my theta map equal to? So this whole, that assuming that this is greater, finally we came to that the mean should be greater than half. And if we write it mathematically in a condensed format, how do we write it? This will be equal to 1 if 1 by n sigma I equal to 1 to n xi is greater than half, and 0 otherwise. Means when the mean is, when the mean is equal to half also, or anything less than or equal to, all the remaining part, right? Then this will shift to 0, and if the mean is just greater than half, then it will go to 1, and that is when our theta is, if the theta is uniform. Assumption is there is equal probability of it being 0 or 1. Okay, so this is the whole maths. I hope this is clear. So we got a point estimate, when it will be 0 or 1, right? So this is clear. So this is your case 1, when the prior was uniform. So I'll write it here, this is uniform, that is equally likely to be 0 or 1. And what was the second case? We did in the last class also. Second case was that it is biased more towards 1. Or let's see another example. We have seen this already. So I'll just change the example. So my case 2 would be that my prior information. So my prior information that I have is probability of seeing theta, 1 is less now, 1 by 4. And probability of seeing theta equal to 0 is more now, 3 by 4. I did opposite now. Okay. So in this case, what did we see? That when priorities are equal, 0 and 1, and there will be a 0.5 in the middle. So if my value is just greater than 0.5, it will become 1. And if it is less than 0.5, then this will become 0. So this region, if my theta falls here, whatever the calculation, the sum of these things come, okay? So if it falls here, theta will become 0, and here if it falls here, theta will become 1, where it was uniform. And let's see, now we have a more prior information that theta is more biased towards, it is having more likelihood or more tendency to be towards 0. It is 3 by 4. and only 1 by 4 towards 1. So let's see how does this impact. So this was with the uniform prior. Now what will be my mapped estimate based on this? So I'll take this all this calculation till log as it is, and then I'll compute from there. So let me copy that where it was. These two terms. I'll just make modifications here, and I'll take it from here. And this time the calculation I'll do it fast so that you understand. So now you have got the hang of it. Now you should be able to follow along pretty fast. This time these values are different. So let me rub things off. So here this is different. These terms will remain as it is, but this time this is not half. Here this is 0 is 3 by 4 and 1 is 1 by 4. Rest of things remain same. Okay, that's the only difference. Earlier it was half, equal. Now this time the prior information is this. So how will we calculate? Again, we want to check that if theta is, for theta to be 1, I want, if theta is 1 means this term should be greater than this term. So we'll calculate it that way. So my bottom term, that is log of 1 by 4 minus sigma I equal to 1 to n xi minus 1 whole square by 2 is greater than the bottom term, upper term, log 3 by 4 minus sigma I equal to 1 to n xi whole square by 2. This should be greater, only then theta will be equal to 1, because the probability of seeing 1 is greater and the log of that will also be greater. So that's what I'm equating to. Okay. So for theta to be 1, this should be greater, and this I have got this equation now. So let's solve it quickly. So this will be equal to, so this will be log 1 by 4. So I am just checking. So I'll bring this, all these terms one side. So this will be log 1 minus log 4 minus sigma I equal to 1 xi minus 1 whole square by 2 minus log 3. I'm bringing it from that side, and minus plus log 4, and this minus will become plus sigma I equal to 1 to n xi whole square by 2, and this whole thing should be greater than 0. Only then my theta will be 1, because the probability of that will be 1. Now let's cancel out some terms. Log 4 is there, log 4 is there, that will go. So this will become log 1 minus log 3. Okay. So this is there. Sigma positive I'll bring here. I equal to 1 to 1. And I'll bring all these terms together. Okay. Half I'll take it common. Xi square minus xi square plus 2xi minus 1 is greater than, I'll take back this side, log 3 minus log 1. Log 1 is 0. Why have I even not? Log 1 is 0. Okay. So we'll get rid of that. So this is greater than log 3. And we have seen this calculation earlier. This calculation. This is the same calculation, right? This is the calculation that we are doing. What did this come out to be? Xi square minus this thing. This is the same calculation that we are doing here. Let me write it down in the same format so that it's clear for you. Half of xi square minus sigma I equal to 1 to 1, or within the same, and we brought this 1 by 2 and outside, right? Minus xi minus 1 whole square. This is the same thing. So this one, what did it come out to be? This is greater than half. Finally this gave me that this mean should be greater than half. Finally we calculated and we found that this should be greater than half. Okay, so we'll just put it as it is to avoid the confusion. So this will give me sigma 1 by n 1 by n I equal to 1 by n xi is greater than half, and this is log 3, so this will be plus log 3 will also be there, because this is already there. So I'll just substitute this value and now this is greater than half, and plus I have, earlier it was 0, and now I have one more log 3 term already, because earlier it was log half minus log half, now this is log 3 by 4 minus log 1 by 4, and rest of the terms come as it is. Okay, right? So when my prior is biased towards 0, now what will be my theta map? My theta map will be equal to 1 if my mean, this is my mean, right? I equal to 1 to n, xi is greater than half plus log 3, 0, otherwise, log 3 by, oh dear, so if it divide it, right, so log 3 by n term will come here. Okay, so after solving this n term will divide here. Earlier it was 0, so that's why it went off. Now this log n will come here. Okay, so just do the maths, you will get it. It's simple, just equating. Okay, so thus log 3 by n term will come. Just solve it step by step, and you will reach here. You will divide at one step, you will divide by 1 by n on both the sides, and then you will get it, this n common that I came up, that I missed out from there. Earlier it was 0, so no problem, but now it is, there is a term, so that's why it will divide this side also, and that's why you will have this. I hope that is clear. So this is our theta map for a biased prior. Okay, and how will this look like on the number line? Say for example, if I have the number line, earlier we said that this is 0, this is 1, and then this is here half. Earlier the likelihood was that if this is this side, but now we have got one more term, that is log 3 by n, half plus. So now this will be 0 till here, and then only if it is greater than this will be in this. So here this will be 1, and here this will be 0. So now if you see, because the prior is more biased towards 0, so my probability, it is extended beyond half, log till log 3 by n. Until this point it will be 0, and only after that. So that's the impact of the prior. And as I said, right, as n grows high, the impact of the prior will be gone, and this will again tend to half only. Right? So this becomes very, very large, so 3 by n will become very small. Okay? And that will tend towards half then. That will become equal to no prior information. Okay? I hope these two cases are clear. So what is the conclusion? For a non-uniform prior. So earlier the uniform prior is there, right? So for a non-uniform prior, my estimate will be pulled towards the prior if it is non-uniform. This non-uniform is this. This is non-uniform. So my estimate is pulled towards the prior, and that's what we are seeing, that it is pulled more towards 0, because it is valid only in the range 0 to 1, and it is pulled more towards 0 than 1. And that extra term is log 3 by n, because that is coming from this probability 3 by 4 and 1 by 4. Okay. So this map is good for, so here map is good for what is that? I'll give you some notes. So this map is good for classification problem. You want one point estimate. Okay. Map is good for classification problems. Classification means yes, no kind of. Yes, no, right, wrong, 0, 1, that kind of. So that's where we can get a binary output, one or the other. So in that case, this will give me whether what is its probability of being 0 or 1, yes or no, right or wrong. Then map estimate is good. Okay. But what if all the real world problems will not be like this? There will be some, for example, my question is, if you have to predict a price of a stock market, so that's a number, right? That's the running number. So there, if I have to estimate, that will not be, this will only give me, I'm making say prediction of some share is some 1,000 rupees, and I'm predicting it as 1,020 rupees, right? So this kind of classification only tell me that whether I'm right or wrong, but it won't give me the magnitude of the mistake I'm doing. So 1,000 and 1,020 is that I'm off by 20. So, but it won't tell me that how much I'm off. So it will tell that whether I'm off by 1,020 or I'm predicting it as 1,200. Both of them are wrong, but it won't tell me the magnitude of my mistake. And what if I want to find that magnitude? So this map won't be sufficient. And that brings us to the next tool, that is our minimum mean squared error estimate. So let's move to the next page. Sorry, I have to minimize, and whenever we do you will see this again, mean square error. This is called MMSE, minimum estimation. This is our second. Okay, MMSE. So this is, so we have to, what is the goal here? The goal is to minimize. I don't want just a yes no answer as a map estimate. Goal is to minimize magnitude of error. Okay, so here the choice is squared error. I'm doing a squared error. I have discussed about that also, why squared error is important and not absolute or just the difference. Okay, so if you have just the difference, right? So for example, if I have a share price that is 1000 and one day I'm making prediction of 980 and one day I made a prediction of 1020, this is minus 20, this is plus 20, and say both the days the cost price was 1000 only. So if I just do a simple sum, then net will be of both the days will be of all the predictions if I'm doing it. So net will be minus 20 plus 20, so will cancel out, and then I'll say 0, that I have made exactly correct predictions, right? So that is not there, but I have made mistake in both the cases. That was off by minus 20 plus 20 minus 20, right? So this is wrong, that I cannot just do a simple summation. So that's why we do a square of it, so that the error term is amplified by square. So this minus 20 will, if I square it, this will become 400, will become 400. So this will give me the magnitude of the mistake I have made, and I want to know how much off I am, how much wrong I am. I want to get that magnitude only, and I want to minimize that magnitude so that I'm close to the value that I want. And that's what all mean squared errors do. It will give me the magnitude, how much I'm off, and if the squaring will just amplify that impact. That's why we go for squared errors. Okay, there are other reasons also. I'll discuss about that in detail when I'm talking about machine learning algorithm, etc. And we have to minimize this. And here again same thing, we are doing an estimation of the parameter, and we have to minimize the, okay, minimize the how much error we are making in the estimation. So if I have the parameter of the distribution of the data, so the net error should be minimized. That's the task. Let's see. So what does MMSE do? MMSE, okay, what does it do? So it minimizes the posterior mean. So posterior mean, okay. So if I find the mean, minimizes the mean squared error. If I find the mean of that, and if that is my estimate, if my estimate is okay, if my estimate is that if I find the mean itself of that whatever is that distribution, so and if that is 1 point estimate, so that will be my minimum, that will give me my minimum error, because this is distance from the mean. If I predict the mean itself, this will minimize the complete thing. So if I have the posterior distribution, and if I predict what is the mean, so all the errors that I am making, this whole net mean square error will be reduced. So I want to predict what will be the mean. Earlier, what did we do for map? We found the peak. Okay, we found the peak. What is the peak of that distribution? But here we want to find the mean of that distribution. Okay, even map, if it's a skewed distribution also, we want to find the peak. But here if I have the mean will be somewhere here. Most of the values this side. Okay, so that's what we want to find, so that our net error, that is the distance from the mean, is minimized. Okay, so what is the task? So how do we calculate mean? The mean is the expected value. Okay, what is the mean? Expected value in terms of okay. So mean is the expected value. So what is my task? The task is to find what is the task? Task is to find expected value expected value of parameter theta, okay, given the data. So I have a data, so I have to find the expected value of the parameter theta given the data. Okay, that is the conditional expectation. This is given. So what is that? That is our posterior, right? So that is P theta given x. This is what we want to find. So I have to find the mean of this. This is we are getting a distribution here, and we want to find the mean of that distribution. Okay. So how we do expected value? How do we write expected value? So my theta MMSE will be equal to minimize. Now we are minimizing arg min theta, and then expected value of the mean squared error. So this predicted theta of x minus actual theta whole square. The expected value of this we want to minimize. Okay, and this will be coming from, this is my posterior. So expected value, so this is the posterior, this is the distribution, this is the distribution of my of the parameter after I have seen the data. So what is the formula for expected value? So if not, check the value or check the video. I'll put the link in the description for the expected value. Okay, explanation what we have done. So this will be equal to sorry, this will be equal to sigma over theta. Okay, and this will be, I'll just write it other way around. So generally this is the probability. Okay, probability of theta. So we see the probability into x, right? Theta given x, theta given the posterior into theta d theta, and if it is discrete, integral over theta f of theta given x, theta given x into theta d theta. This is for discrete, this is for continuous. That's what we do, right? The values of the theta into their probability, value of the theta into the probability, and the summation overall for discrete, and the complete integral over the range of that theta. That will give me the expected value. This is how we do expected value. Probability into that x, probability of x into x. That is my expected value. I hope you remember this. That's what it is. Okay. Now let's. So for as the examples that I'm talking, we have discussed this already, and I have been mentioning this. Watch the previous recording. In that it will be present, and I'll take the example as it is, and I'll then proceed from here. So example 1. Example 1. So discussed in previous video. Watch that. Without that it is not there. So I'll just give you highlights of that. Okay, so what was the prior there? Prior was f of theta is equal to 1 uniform 0 over, okay, and if I want to write, so it introduces beta function also. So this same thing in this is beta 1 1. Okay, this was uniform. So this is beta 1 1, or I can, in terms of uniform, I can write theta is uniform 0 1. This is uniform in this range 0 to 1. Okay, this is my prior. What was my likelihood? So what, after this we calculate the posterior likelihood, etc. See the calculation there. Okay, calculations prior, posterior. What was the posterior there? F of theta given x, is equal to this was, okay, so let me write it down so that it's clear for you. So the likelihood was Bernoulli. So this was Bernoulli. The underlying distribution was, assumption was, the distribution of the data was Bernoulli. So we are doing Bernoulli trials. So their likelihood of f of x given theta was equal to theta to the power n1 minus theta to the power n minus 1. where n1 is number of ones. n1 is equal to number of ones in n trials, and n minus n1 will give me number of zeros. Number of zeros. So this is theta was probability of 1 success, and this was probability of failure, and we have to find this parameter theta. And after doing this analysis, we found out that posterior was, what was the posterior value, and we discussed about beta functions also there. So that was theta n1 1 minus theta n minus n1 by beta of n1 plus 1 and n minus n1 plus 1. Okay, and what is our beta? Just to give you this is integral 0 to 1 t to the power a minus 1 and 1 minus t to the power b minus 1 t of t. So this is our beta function. So this is a beta function or beta distribution that is used to simplify complex integrals, and we used it as it is where our integral was there. As I told you, calculating the integrals are difficult, and we use known distributions, and beta is one of them. This is called beta function or beta distribution. Okay, and if we plug this in, and then after this we got that this is a beta function with n plus 1, n1 plus 1 and n minus n1 plus 1 when theta was uniform. Okay, and now let's calculate. So this is known. So till now we have done in the last video. Now let's calculate. So we know the distribution, everything. So this gives me the distribution of the posterior. So I have got the distribution of the posterior based on the prior. Okay, so what will be the MMSE now? Theta MMSE. So I want to get one value out of that. What will be my minimum mean squared error? For which theta in this distribution will I get the minimum mean squared error? So I have to find the mean around which. So this will be integral. So this is a continuous. I'll do an integral 0 to 1. Okay, and this will be theta into the probability distribution. See, I have multiplied theta here. Theta. So this is a multiplication of theta and probability. So this is your posterior into theta. So I have got the posterior and I multiplied with theta. So theta I have done multiplication, and let's multiply it with the posterior. What is the posterior? Theta to the power n1 minus 1. No, n1 and 1 minus theta to the power n minus n1, and this integral is also there. Theta is in the range 0 to 1 because it is uniform. This integral will be in the range of 0 to 1, and this is divided by the beta function that we had, n1 plus 1 and n minus n1 plus 1. Okay, so what will be this value? This will be equal to, so this theta will come here, so this will become 0 to 1 theta of n1 plus 1 minus theta n minus n1 remain as it is, and this is a beta function already, n1 plus 1. Okay, and this is n minus n1 plus 1. So this is again a beta function because this is the integral theta and 1 minus theta. This is an integral n minus, and what is the format? A minus 1 is equal to n1 plus 1. So let's find what will be the parameters a and b of theta. So you have to find a is equal to a minus 1. A minus 1 is equal to n1 plus 1. This implies a is equal to n1 plus 2. Similarly, b minus 1 is equal to n minus n1 plus 1. So b is equal to n minus n1 plus 2. Sorry, n minus n plus 1 was not there. 1. This is only 1, right? So I have to make to compare to only this. Here n plus 1 is there, and here n minus n1 is there. So n minus n1, this one will come here, and then this 1 plus 1 came here, 2. So what will be my beta distribution corresponding to this? A is n1 plus 2 and b is n minus n1 plus 2. So my theta predicted, so I'll put a hat, this is prediction symbol, is equal to, in the numerator is a beta function of n1 plus 2 comma, this is a, and b is n minus n1 plus 1, and the denominator is beta of n1 plus 1 n minus n1 plus 1. This is for uniform prior. Okay, I hope this is clear. This is simple. So we just calculated the mean or the expected value, and the expected value was is the posterior into theta into because the expected value of something is probability of x into x, and this is summation or integral, whatever, depending upon the case, and this will give me the summation of the whole range will give me the expected value, and that's what we did with the posterior. After when we have got the posterior, we have got the distribution. That means that is giving me the probability distribution. Multiply it with the each value of the theta, and then get the value out. And we got that this is this value. Okay, and let's do similarly for the example 2 also. Similarly for the example 2 from previous video, where the theta was biased towards 1, previous video. Here I'll take the same example. So my f of theta is equal to 2 theta. 0 is less than x, 1 0 otherwise. This is my prior. Okay, so this was my prior earlier. So similarly, if you calculate this, so this is my prior, same thing, and now you are seeing that this is 2 theta. So I just calculate the posterior quickly. So my posterior will be, what was the posterior for that case? I'll just refer from the last class. F of theta given x is equal to, this was theta to the power n1 plus 1 and 1 minus theta to the power n minus n1, and the denominator was a beta function of n1 plus 2 comma n minus n1 plus 1. Okay, so this was my posterior. So posterior is already there. Okay, right. So after this I have to calculate my theta MMSE, theta predicted MMSE. Similarly, it will be expected value of theta into the posterior. Posterior is here, and the integral will be 0 to 1, and after you do the calculations yourself, this will be similar calculation as it is, and what we will get finally is, this will be a beta function of n1 plus 2 is here. Okay, and this will increase by further one more, so it will become, if I multiply by theta here, right, I will do it quickly for you. Integral 0 to 1, this is 2 theta into theta n1 plus 1 minus theta n minus n1 plus 1 by, this is beta of n1 plus 2 comma n minus n1 plus 1. Okay, and this 2, and here also that 2 will come. Okay, this will cancel out, and this theta will increase 1, because this theta will multiply here also, both of the places. So this will become, and this will become finally, just do the maths, this will become a beta function of n1 plus 3 n minus n1 plus 1 by beta function of n1 plus 2 n minus n1 plus 1. So this is your theta MMSE, that is minimum mean squared error for that estimate. This is your estimate. Okay, this is your estimate. I hope this is clear. So this is for the biased, this is theta is more biased towards, you remember this was this y is equal to 2x or theta is equal to 2 theta. So as you go towards 1, this is more biased towards 1. That was the distribution of that theta, and this was uniform. This is your minimum mean squared error estimate for, this is different from the uniform case. This is for uniform prior, and this is for biased prior, biased towards 1. We saw both the cases. One in the first one, in theta map, we saw bias towards 0, and in MMSE we saw bias towards 1. So that it gives you idea. It can be prior, can be biased towards any of the values. Okay, and depending upon that, we will get the final outcome. Some notes around this. So where theta map and theta MMSE, some important things to note around this. So if sorry, if your posterior distribution, whatever we got after distribution, right? So if this posterior distribution, if this is symmetric, then like a Gaussian, if it is symmetric, okay, then this your map and MMSE will be very close or maybe same, okay. And this will be this is unimodal also. Unimodal means there's only one mode. Unimodal means one mode, means only one value has the highest frequency, okay, that is around the mean. So your map and MMSE will be same when this is symmetrical and unimodal. Okay, that's obvious also, because map is the map is around the highest frequency value or your peak of that, and if in the Gaussian you see that is the mean also. So and all my MMSE, what we are trying to minimize is the error from the mean. So if my expected, the estimation is the mean itself, so both will coincide and theta map will be equal to MMSE if it is symmetrical and unimodal, one mode and it's symmetrical. But what if it's not symmetrical? So if it's not symmetrical, say for example if it's skewed, then MMSE and map will not be same, okay. That can differ a lot. So for example, if my distribution is like this, it is skewed towards right like this, so now my peak will be here, but my mean, because this is heavy tail, so my mean may be maybe somewhere here, I don't know. So this can be my map and this can be my MMSE, okay. If it is skewed, then this will not be same, it will be pulled towards the skew, okay. So that is the case, so just remember. And there can be cases when there are more than one modes, okay. Multimodal is not, so multimodal means there are more than one mode of a distribution. So this is not uniform also, and say something like, right, so there are multiple peaks. So which peak? Okay, so in this case your MMSE makes more sense, because there are multi-mode, which mode to check. So that time you should choose, okay, that this is this theta map, okay, the map estimation does not give a good estimate, then that time you should check the MMSE. So this is a use case, so that you understand depending upon the posterior distribution what kind of metric and what will be the impact of that metric, because map is giving you only the peak value, and in case of MSE it is calculating the value of each of the points, okay, each of the points with respect to the mean. So it is taking more points into account. Here it is taking, map is taking only one, but MMSE is taking all the points into account for calculating minimum mean squared error, okay. So this is a more robust metric. MMSE is more robust because it is taking more points into account, okay. So that's the thing, especially for skewed or whenever it is that when this posterior distribution is skewed, or if it is multimodal, then always go for MMSE, because that is a more robust metric than map, okay. I hope this is clear, okay. There's lots of information. Just do a quick revision of what we have done. So in this video we were doing Bayesian point estimators. This is a continuation of parametric model estimation, okay. So we are trying to do the get point estimate of the Bayesian inference that we had. That the Bayesian inference gives us a probability distribution of the random value. So it considers the parameters as a random variable, and it gives me the distribution, final distribution. And so, but what if I want only one point value? So for that only this whole discussion was that there are two this is most popular, and then even this is used for this is for classification, this is for regression kind of problems where we want the exact magnitude of the error. Here this is just for true or false, 0 or 1, yes or no kind of answer. Then this is good, this will one point estimate will work fine. But here if you want to find the magnitude of error of multiple errors, then MMSE is used, okay. That's the broad understanding. And then we saw, okay, this is the Bayes theorem. Depending upon that, then we saw two examples of the map. For map, one was when we played with the Gaussian distribution where the theta, which was the mean, was unknown, and we tried to predict that. The initial belief was that it is uniform, and then finally we found out that on the first calculation that if theta is greater than half, then this will be 1, and if it is less than or equal to half, then this will be a 0. And then in the second case we discussed that the prior information was that theta is more biased towards 0, and based on that prior we found out that yes, that is correct, and the new estimate came out that it had one more term which was log 3 by n, and we saw the calculation here, and that pulled the theta towards the initial belief. Okay, it was earlier with uniform distribution where everything is equally likely, so I don't have, that is no information, right, when everything is equally likely. But when we have some real information that theta is more pulled towards 0 or more probable towards 0, then that pulled the posterior or the estimate also, the theta map also towards 0, and we have more likelihood of getting a 0 than a 1. Okay, and then we saw that map is only good for classification. Yes, no kind of problems. What if we need a magnitude of the error? Okay, then we went for minimum mean squared error estimation, and we found MMSE for 2 cases. Okay, which is MMSE is just the expected value of the mean squared error, where we have the posterior distribution into the value of the theta, and we do an integration or summation over all the things as we do for expected value, and then we calculated that. For both the cases, for the example that we have discussed in the last class, one was for the prior as uniform, and the other was prior that is more skewed or biased towards 1, and we found out the beta functions for that. In terms of beta functions, we got the theta MMSE, the predicted value. Okay, and then we saw that which metric makes sense. So if the distribution, the posterior distribution that we get, that is symmetrical and unimodal, that it has only one peak, then map and MMSE will mostly coincide, that will be one value. But if the data is skewed or the post distribution is skewed, then this map and this will differ a lot. That will depend upon the skewedness. And if you have multimodal data where there are multiple peaks, then MMSE makes more sense because it takes mean into account. So map is mode based. So map is mode or peak based estimate, and MMSE, that is in a nutshell, that is mean based estimate. Okay, and these two can differ for a distribution. That's the nutshell understanding. Okay, that's all for this video. Thanks for watching this video. Have a good day and bye for now.